All right. Hello, everybody. Thank you for your patience, and yeah, thank you. You're still here. So I'm going to present today our understanding, how we understood atomic layer deposition approach to synthesizing copper zinc tin sulfide solar cells. So this work was done at Argonne National Lab collaboratively between two groups, surface chemistry group and atomic layer deposition group and energy science division. My narrative will be like asking questions and answering them during showing some information on my slides. So first question is why CCTS? As was just recently shown in several publications, 2010, 2011, 2012, CCTS, first of all, it has very decent band gap of approximately 1.4 electron volts, and which still stays tunable. As was shown in a nice introduction to my talk by Rakesh Agrawal. They can mix, they can make solid solutions, and they can tweak. Oh, okay, sorry. And they can tweak energy gap, changing it. I'm not telling anything new here because I mean the most famous example would be like gallium arsenide, aluminum gallium arsenide when you change this band gap. So right now it's shown that efficiency of these solar cells are exceeding 8%, and it's still plenty of room for increasing it because open circuit voltage is still below its maximum, and short circuit current is also still below approximately 33 milliamps per square centimeter. What's going on here? Doesn't work? Now it's better? Okay, so and main thing is that you can build these solar cells from abundant elements, which brings you to the low price of solar cells on the mass production level. And here I just want to show you this fingerprint Raman spectra of CCTS, which was like shown in one publication of one of groups working on CCTS in IBM. So here I want to just briefly outline first today atomic layer deposition route to CCTS. And so idea behind is like to take three different binaries, which is tin sulfide, copper sulfide, zinc sulfide, create a multi-layer structure, and then anneal it at high temperatures, melting it in CCTS structure. So, and since we have three different binaries, you can think of 6 different ways of growing 3-layer stacks by atomic layer deposition. So, but it appears that first 3 of them, they fail because of copper-tin nucleation failure. So basically copper sulfide just doesn't grow on top of tin sulfide, zinc sulfide, and again tin sulfide in this arrangement. Second 2, they fail due to so-called ion exchange. When you say you grew your layer and then you try to grow next layer on top of pre-existing one, and so you start to bring cation precursors, LD cation precursors, and it happens that precursors brought, it basically kills and grabs the whole pre-existing layer and removes it from the substrate. So that's what happens here. So in first case, basically when you deposit in zinc sulfide on top of copper sulfide, copper sulfide and zinc sulfide, there is a full removal of zinc. And in second case, you just, instead of copper sulfide, you get pure copper metallization. So, and here we go. We have only last one version of this 3-layer stack approach, which actually works finally. So, and when you grow this, it might be quartz, it might be silicon substrate. When you grow this when you grow your layers in this arrangement and then you anneal in excess of 400 C, you obtain CCTS. So, and it's shown here, this is Raman spectra of obtained solar cells, which actually showed photoactivity. So, and specifically in green light, they showed external quantum efficiency of 16% and external quantum efficiency is 5%. And here you can see for the current, this measurement was done in potassium chloride solution with europium 3+ electron acceptor with silver counter electrode. Then the next question, why again we need atomic layer deposition here? So there are several answers for that. First one is of fundamental interest because again, as was mentioned today, the best performance shown by CCTS solar cells, which are zinc enriched and copper deficient. And this plot shows how you can tweak by changing cycle ratios in ALD growth process, ratios between copper and tin and zinc and tin. This is areal density measured by X-ray fluorescence. So, and keeping the ratio between zinc and tin approximately 1.2, you can go up and down in terms of this ratio. And enriching in copper, it gives you low efficiency as shown here, and in copper deficient solar cells, you have higher efficiency. And this is because you basically has a nice way to interplay between copper zinc anti-site when copper sits at zinc site in the crystal lattice, and between copper vacancies. So copper vacancies, they have, these are shallow defects with energy approximately 0.01 electron volts, and copper zinc anti-site, it has 0.1 electron volts. So copper vacancy is a shallow defect. That's why performance in copper deficient solar cells much better. So the second thing is that you can cover with ALD high aspect ratio substrates. Here is a silicon trench covered by 3 layers through ALD, and then it's melted into CCTS. And these are 2 magnified plots showing top of this trench and bottom of the trench, and you can see these numbers. So it's basically very nice reproducibility of thickness of CCTS film. So, of course, to grow very thick layers, like also it was shown, like approximately 500 nanometers or even 1 micron is very hard for ALD because it's basically 100 nanometers. Sometimes it takes 24 hours. But the point is that thick films, solar cell films, it doesn't always mean that it's bad. So in some cases, thin layers and ultra-thin layers can show even better performance, because one of the ideas to do that is because of when you have thin layer with respect to thick version, band bending is very much less, and your open circuit voltage, which is the difference between Fermi level of electrons and holes, stays bigger, and band bending is not terrific, but the layer of CCTS, which is p-type semiconductor, is still thin enough, and you can effectively collect your electrons and bring them to the external contacts. And and at the same time you keep short circuit current on the same level, and you increase your open circuit voltage, and you basically comes to the better efficiency because it's like multiplied current by voltage fill factor divided by intensity of your light. And the second example would be, so if you use plasmonic metals antenna covered with very thin layer of solar cell or semiconductor, it was shown in 2010 that using this approach you basically can cover these plasmonic nanoparticles, metal nanoparticles, with very thin semiconductor layers, and by doing this, you can basically save like 1,000. You can use 1,000 times less semiconductor that it would be like using just the bulk thick layers for effective absorption of light. Because plasmonics does this job, so light is trapped in this nanoparticle antenna, and then the whole light is effectively absorbed by a layer of semiconductors on top of it. So, and yeah, of course, both problems are very nicely suitable for atomic layer deposition capabilities. So also what is known that LD is very good, and several talks show this today, that it's very good in metal oxide deposition. So, and it just, from 90s even, it's known that by growing metal oxide by ALD, you can get nicely defined so-called nanolaminates. It means you have very sharp interfaces. So it's still some interfacial roughness, approximately 1 to 2 nanometers, but it's pretty good. So, and this plot just shows independence of interfacial roughness when you increase number of double layers in this nanolaminate by ALD. So ALD metal oxides are nanolaminate as known. Okay, now I want to briefly describe our approach to the next investigation in what follows. So this is our secondary ion mass spectrometry, and we're doing so-called dual beam mass spectrometry. So basically we have two separate ion beams. One is just for milling and the second one for analysis. So we repeat these cycles, one for milling, and then we reveal subsurface, and then we use pulsed argon plus ion beam to probe this revealed surface. So, and then under this pulsed ion beam, plume of secondary ions goes to our top mass spectrometer, and then we generate this pattern of mass spectrum. It seems intensity versus mass. This ratio just shows that arrangement is such that depth resolution of our dual beam system is mostly controlled by milling low energy beam, and we do our ion milling with 250 electron volts only, keeping it focused and high current. And so this ratio alpha, this is, so if we keep it low, it means our depth resolution is controlled only by milling beam, and also we can nicely control ratio energy spread of our milling beam to its nominal energy. And when I say we sputter at 250 electron volts, it means that our beam is monoenergetic to extent of 1/10. And also we pre-select pure argon plus ions by Wien filtering of both guns. So, and also, yeah, this is one more plot showing how we deliver our beams, and also we have electron microscope attached to this. And also, again, I think I'm going to go to the next slide. Atomic layer deposition group, they grew for us metal oxide nanolaminates. Basically, it was 8 pairs of magnesium oxide, zinc oxide. And what we showed that we could resolve all the layers in this nanolaminate. Also, we have this high resolution pre-surface plot where we show that we basically, when we decrease time intervals of sputtering, we basically can reveal surface contamination with magnesium from first magnesium oxide level and reconstruct surface contamination from the depth profile of this layer. And also we can do some simulation, and what we learned from this, from doing high resolution seams of metal oxide nanolaminates, that we can estimate our depth resolution of our seams as 0.5 nanometers. And also we were able to learn something of nanolaminates themselves. So what we showed that the flat thickness of this nanolaminates growing by atomic layer deposition was only 3 nanometers, and interfacial roughness we showed it was 0.5 nanometers. So it was just purely done by depth profiling experiment, which also was proven by X-ray reflectivity, these numbers. So And what was known, and by SIM it's known that metal oxide are nanominates, so in this work we also address this question, are metal sulfide nanolaminates, how sharp are the interface between ultra-thin metal oxide, metal sulfide multilayers deposited by atomic layer deposition? So, and it comes to the second question, like, should we target nanolaminates or homogeneous multinary compounds by doing ALD synthesis of these 3-layer stacks, or should we target only purely copper, zinc, tin sulfide solar cells? And also, it's very important to address this question, like if we do heterojunctions between zinc oxide and CCTS and zinc sulfide CCTS, which is P-type semiconductor, and these guys are N-type semiconductors for electron harvesting from the system. So, and here we introduced so-called mixing number, which is a ratio between interfacial sharpness of the interface and the layer thickness. So this mixing number is ratio between diffusion length and the thickness of the layer. So, and it may be mutual diffusion under growth condition. When you grow next layer on the pre-existing layer, this layer can penetrate inside the layer being deposited, and as well as layer which is being deposited can at the same time penetrate into the pre-existing layer. So, and here are some, so in this case, this thickness layer would be like thickness of the pre-existing layer, and in the second case, when the layer being deposited penetrates in the layer, pre-existing layer penetrates in the layer being deposited. In this case, thickness of the layer is number of cycle of ALD multiplied by growth per cycle, which is like thickness of the film which you can grow per single ALD cycle. Here is some example which shows that if it would be an investigation of copper diffusion into cadmium sulfide, so our mixing number would be 1.5. So, and this mixing number basically means, so when mixing numbers is way much less than 1, it means we have nanolaminate, which is the case for metal oxide. We have sharp interfaces. When it's close to 1, we have diffused interfaces, and when it's much larger than 1, we basically have completely homogeneous mixed layers, which you also can get by annealing nanolaminates under high temperatures, okay? There are several routes. This is an experiment, so we used silicon substrate on which it was 190 cycles of anion precursor H2S coupled to this precursor, cation precursor, which I cannot reproduce its name. Then 800 cycles of, again, H2S with the precursor for tin, and then 290 cycles of anion precursor H2S with diethyl zinc, which is zinc precursor. So this growth process took place at 135 C for 14 hours, and then to obtain CCTS, we did different annealings at 275 C, 350 C, and 425 C for approximately 1 hour. So this is a signature, this is X-ray reflectivity of 3-layer stack of which are copper sulfide, tin sulfide, and zinc sulfide. And that's how we calculated so-called areal densities of the material. And then you can recalculate using this number of cycles and areal densities measured by XRF. You can recalculate expected thicknesses of each of the sulfide binaries which were grown by ALD. And then also we do these annealings, and also we look at these samples as well by doing the same dual beam high resolution time of flight mass spectrometry. So, and these are typical mass spectrum for our samples. So what we learned from this is a as deposited case, this is annealing temperatures, which I just mentioned. So for all the next slides, you will see that all the layers are heavily diffused. So which means basically there are no almost interfaces between metal sulfide binaries. So, and you can easily see that copper, this is basically, these boxes, gray boxes, they show prescribed morphology that one would expect by doing X-ray reflectivity and recalculating it purely in thicknesses of the metal sulfide binaries, assuming that metal sulfide binaries should be non-laminate, okay? So you see that copper sulfide layer is much thicker than expected, and also it goes all the way through the whole structure. So copper is very diffusive, which means that it's very natural that when we heat the structure up to 275 C, we already see that copper is evenly distributed through the whole bulk of our solar cells of the CCTS. And once we increase temperature, copper becomes more and more homogeneous. So this is the hottest temperature. So this is just completely plain profile of copper. So this plot is seams intensity, which is just integral over copper peak 63 versus depth when we sputter. So the same story with tin, and it's shown here that tin sulfide layer is way much thinner than one would expect. And with respect to the previous slide, it basically says that the interface between these two layers was shifted towards the surface of the film, of the CCTS film. Also, we grow in our anneal temperature, and we already see that at under 275 C, our tin is evenly distributed through the whole structure, and we just increasing the temperature, and tin becomes more and more flat. But there was only one sharp interfaces with the interface position exactly when was expected. So this is the interface between zinc sulfide and tin sulfide. And we see that it's very sharp, abrupt. And also it's also seen that once we increase the temperature of annealing, so under 275 C, zinc doesn't go really far towards the substrate, still keeping this peak, which is zinc sulfide layer. So, and once we increase this temperature, also under 425 C, we can reach some sort of planarization of zinc profiles through the whole structure. And we interpreted this effect in terms of predicted some time ago effect, which basically says that solid state reaction between these three metal sulfide binaries takes place in two steps manner. When you under annealing mix copper sulfide, tin sulfide, and zinc sulfide, first you mix copper sulfide and tin sulfide, and it creates this compound. And once you proceed with increasing the temperature, only at that time, basically somewhere closer to 400 C, zinc sulfide starts to penetrate in this three-component material, and finally under 425 C, 450 C, it creates like nicely defined copper zinc tin sulfide material, which also was proven independently by XPS and by Raman spectroscopy. Okay, so sulfide is basically showing the same trend, so it seems like it plays a very important role in this mixing procedure. And also what we did, we were able to estimate mixing numbers and diffusion coefficient doing this high resolution seams of initial binaries, and also we were able to find best starting annealing temperature for mixing these binaries into perfectly aligned CCTS material. Yeah, so we basically determined these diffusion coefficients by doing these slopes. These lines, this is semi-log plot. These lines are diffusion length, and in case between tin sulfide and copper sulfide, our diffusion length was this delta, which is basically shift between expected interface position and measured interface position. So, and diffusion coefficients appear to be not really huge, but time needed to LD growth of these materials basically brings you to very much mixed metal sulfide binaries. Okay, I'm gonna skip this. So we basically grew this heterojunction and we showed that zinc sulfide is much better in terms of stopping of copper, tin, and zinc penetration in towards the surface. So, and here are our conclusions. So far, the only targets for LD is pre-mixed metal sulfide binaries, and the only target is then anneal them to get pure CCTS material. So we also showed this two-step solid state reaction, and also we showed that zinc sulfide is much better in terms of creation heterojunction for devices application, and probably titanium oxide would be better, but we never tried it. So, and I want to thank my colleagues, Alexander Zinoy, Emil Triplett, Jeffrey Clark, and two other guys from Atomic-Layer-Deposition group, Qingpeng and Neil Manet. So, thank you.
Let's quickly thank the speaker.